Hello, everyone. Thank you for joining my presentation today. My name is Yiding, and I am from Florida International University in Miami. Today, I'm excited to share our new approach to renewable energy aimed at combating global warming. On this slide, you will see a couple of photos of our campus, complete with lakes and palm tree that Miami is famous for. Stop right. Let's start with why this research is so important. Despite decades of development, renewable energy still plays only a minor role, with fossil fuels powering over 80% of the world. Solar panel and wind turbine have their limitation, like inconsistency and load output at times, which means we still need a massive energy storage solution. Each year, we consume over 16 billion tons of fossil fuel. To replace just 2 weeks of this with renewables, we would need about 61.4 billion tons of storage capacity. That's not just a big number. It is a massive challenge, especially considering the environmental toll of battery production for such a scale. Using battery on a large scale for grid power storage can lead to considerable environmental harm during their mining, manufacturing, and recycling process. Additionally, these batteries compete directly with electric vehicles for resource, which conflict their usage in grid storage. Furthermore, the on-site combustion of fossil fuel, including for industrial heating, contribute to over 27% of global greenhouse gas emission. This level of emission rivals those from traditional power generation, yet it remains largely unaddressed by current renewable energy strategy. This strategy is a natural-based solution, NBS, to tackle global warming, a problem rooted in natural processes. It proposes simple, naturally fix utilizing water for storage and air-water system for power generation, avoiding harmful chemicals typically used in other processes. This method allows for eco-friendly and economical energy storage and generation at a low temperature on a large scale. In particular, the utility-scale underground hot water storage system serves as an alternative to fossil fuel, providing a reliable source of thermal energy for power plant and heating for both industrial and residential applications as needed. Our air water power plant can generate a stable more than 100 megawatts of power using hot water stored at nearly 100 degrees C. This system replaces traditional fossil fuel power plants, ensuring consistent power supply regardless of weather conditions. Overall, this approach not only significantly reduces environmental impact, but also cut costs for both power and heating, helping to phase out fossil fuel with a sustainable all-natural solution. To illustrate, consider our underground hot water reservoir system. On the left, you see a top view of a reservoir with its structure supports. And on the right, a cross-section showing how the hot water, soil insulation layer, and the potential possible installation of the solar connector on the ground surface. Let's talk about sample calculation results of the underground storage system. First, our storage system is incredibly efficient, storing over 80 times more energy per kilogram of water than traditional methods like pumped storage hydropower. and compressed air energy storage. If the size of storage system, underground system reservoir has a dimensions of length equals 500 meter, width equals 500 meter, and height equals 15 meter. The hot water temperature is at 120 degrees C. The thermal to work conversion efficiency is 10% only. And the water temperature drop before the recharge is 40 degrees. The total work storage capacity is about 1.75 times 10 to the 7 kilowatt hour. For a power plant of 100 megawatt capacity, the stored energy can sustain the operation continuously for 7.3 days before recharge is needed. The underground storage system can maintain the thermal energy content of the stored water for years. Therefore, renewable energy can be extracted and stored at any time year-round. In particular, during non-peak demand periods or season, and be used whenever needed. The construction costs are more than 70 times less than lithium-ion battery storage system for power grid. For example, for the same storage capacity of the reservoir of 1.75 times 10 to the 7 kilowatt hour, the construction cost of the reservoir can be less than $100 million, while the corresponding battery cost could be more than $7 billion. More importantly, the underground storage system can last hundreds of years versus 10 to 15 years of battery. The underground storage system could also be an integral part of the global freshwater strategy because the storage would conserve the water that would otherwise be depleted due to evaporation into the open air. It causes no environmental impact or risk to the surrounding community and could benefit their ecological system. We are also exploring underground tunnel storage solution, which could be integrated into mountains area, use tunnel boring machine, enhancing our capacity, flexibility in storing and utilizing hot water. Turning to how we connect energy, our starting point is using both direct and diffused solar energy with cost-effective, non-concentrating solar conductor. For the conductor's output temperature to be above 100 degrees C, we still have good connector efficiency. Higher temperature evacuated flat plate connector as well as the concentrator augmented tubular solar connector using compound parabolic trough connector CPC for water production. This figure shows the performance curve of commercially available high-performance evacuated flat plate solar connector. If the ambient temperature TA is 30 degrees C at an operating temperature of above 190 degrees C, the non-concentrated solar conductor efficiency is still above 50%. For even higher water temperature, the concentrating solar conductor that are typical for concentrated solar power may be utilized. Let's turn to air-water thermal power plant. First, talk about background. We have air-water thermal power plant working with low temperature source based on Office of Renewable Energy Efficiency and Renewable Energy. Geothermal energy resource below 300 Fahrenheit or 149 degrees C represent the most common geothermal resources. Thermal power plant that could enable the use of vast amount of thermal energy resources at low or medium temperature to generate electricity on a utility scale could have a significant impact on the advancement of renewable energy. However, this kind of power plant at present is not available, even if some organic Rankine cycle power system using isotope, pentane, ammonia, or refrigerant have been developed in the past 40 years. However, the use of hazardous substance working at very high pressure and generally high vapor density had a limited power capacity within 1 megawatt level and a thermal efficiency of about 10%. For this reason, the concept air-water thermal power plant is conceived. The air or combustion gas is the exclusive working fluid of conventional gas turbine-based power plant. The heat acquisition before the expansion in a turbine is through sensible heat, which may require more than 1,500 degrees C, through the combustion of fossil fuel to attain sufficient sensible heat for high turbine power production. Water is the exclusive working fluid of conventional vapor power plant under closed cycle operation. Any meaningful accumulation of air or non-condensable gas is not tolerable and must be removed by vacuum pump, which may require a heat source temperature slightly higher than 100 degrees C. In analogy to positive electric charge and negative electric charge, and from philosophic point of view, the air and water may form a couple. One is positive fluid, while the other is negative fluid, and vice versa. Their intimate interplay is essential to life and ecosystem on the Earth. For example, their interaction facilitates the water cycle in meteorology, which has significant importance on the climate system and ecosystem. The intimate interaction between hot water as an energy source fluid and air as an energy receiving fluid could enable energy acquisition before the expansion in a turbine under reduced temperature difference and open cycle under turbine platform. Using open cycle turbine platform to generate utility scale power, the most important action is to raise the enthalpy at the inlet of the turbine, which may include both sensible heat and latent heat. For conventional gas turbine power plant, the first term on the right is the sensible heat that could be very high because the gas temperature could be more than 150 degrees C. And the latent second term is negligible. For air-water power plant, however, the first term is negligible because of the low temperature. However, the latent heat term is huge because the huge value of HFG, around 2.4 times 10 to the 6 joule per kilogram. Table 1 shows the contribution of latent heat to the inlet enthalpy, which could be above 98%. Now let's discuss how an air-water power plant works. There are two options. One is frontal compression, as shown in this figure. The ambient air is induced into the power point from the bottom and enter a compressor system, where it is compressed to a higher pressure. The compressed air then enters a direct contact mass heat transfer packing. At the same time, the hot water is pumped from the underground storage into the power plant packing, which flow downwards in direct contact with the upflowing air. Direct heat mass transfer occurs between the water and air, and some of the water is evaporated into vapor, and the vapor enter the airflow stream, so that at the outlet of the packing, the air airstream is essentially an air-vapor mixture. The air-vapor mixture with a high latent heat then enter turbine to expand and produce power. After expansion, the air-vapor mixture exits the turbine but still contains a substantial amount of vapor at relatively high temperature. For this reason, the mixture then enters a regenerator condenser. Simultaneously, the hot water entering the packing exits the packing from the bottom as a cold water stream near the ambient temperature. Because the vapor mass transfers into the air, this cold water is pumped to the top of the regenerator to enter the regenerator condenser to recover the water and heat from the upflowing air vapor mixture. In the regenerator, the mass and heat transfer are from the air vapor mixture to the cold water. Finally, after recovering water and heat from the mixture, the water exits the regenerator and then is pumped back to the storage for thermal recharging, while the air vapor mixture with minimized vapor content and reduced temperature exits the regenerator from the top and discharge into the ambient as exhaust flow stream. Table 2 summarizes the performance of the frontal compression operation. As at a hot water temperature above 130 degrees C, the power capacity has reached about 170 megawatt, with a plant thermal efficiency of 15%. But as the hot water temperature is reduced to about 100 degrees C, the performance degrades significantly, with a power capacity of about 20 megawatt and the efficiency of about 12.5%. This figure shows the second option of the real compression. The ambient air is induced into the power plant through the bottom and enter direct contact mass heat transfer packing without being compressed. At the same time, the hot water is pumped from underground storage into the power plant packing, which flow downwards in direct contact with upflow air. Direct heat mass transfer occurs between the water and air, and some of the water is evaporated into vapor, and the vapor enters the airflow stream so that outlet packing, the airstream is essentially an air-vapor mixture. In this case, at the inlet of the turbine, the pressure is near the ambient pressure. To create a sufficient expansion ratio for the turbine, a real compression system is installed at the top of power plant after regenerator condenser, which creates a vacuum condition at the outlet of the turbine. The air vapor mixture with a high latent heat then enters the turbine to expand and produce power. After expansion, the air vapor mixture exits the turbine but still contains a substantial amount of vapor at relatively high temperature. For this reason, the mixture then enters a generator condenser. Simultaneously, the hot water entering the packing exits the packing from the bottom as cold water flow stream near the ambient temperature because the vapor mass transfers into the air. This cold water is pumped to the top of the regenerator to enter the regenerator condenser to recover the water and heat from the upflowing air vapor mixture. In the regenerator, the mass and heat transfer are from the air vapor mixture to the cold water. Finally, after recovering water and heat from the mixture, the water exits the regenerator and is then pumped back to the storage for thermal recharging. While the air vapor mixture with minimized vapor content and reduced temperature exits the regenerator and then compressed to near ambient pressure by the rear compressor system to be discharged into the ambient as exhaust flow stream. Table 3 summarizes performance of real compression operation. At a hot temperature about 100 degrees C, the power capacity has reached 300 megawatt, with a plant thermal efficiency of 16%. Therefore, real compression option favored operation at a lower temperature. Analysis show that use the chiller to cool intake air in the summer or the inlet air to the compressor could have significant benefit to the performance of air water power plant. Our calculation have shown that a that an underground hot water transportation pipeline with a diameter 1 meter and a barrier 3 meter deep lost less than 4% of its thermal energy over distance exceeding 100 kilometers. This efficiency supports the development of so-called Internet of Hot Water, Power and Heat. This picture shows that the storage system acts as a hub connecting various energy source and user. Hot water could be sourced from solar farm, industrial waste heat recovery system, and a geothermal well, then stored underground. The stored hot water could then be distributed to the power plant to generate electricity, or used to supply low-temperature water to water treatment facility. Additionally, it can provide hot water for residential heating in city for agricultural use in rural area. We also have a discussion and conclusion on this slide. And next one. This slide concludes discussions and conclusions. Finally, more detailed technical information can be found through the following two publications. Thank you very much for your kind attention.